Welcome, everyone, to the Intel Builders webinar program, and thank you for taking the time to join us today for our presentation titled Delivering N-Memory Database Performance on Intel Flash. Before we get started, I want to point out some of the features of the BrightTalk tool. There's a question tab on your screen. I encourage the audience to please type in your questions at any time during the presentation. Our presenters will hold off on answering those until the end of their program. On your viewing screen, you'll also find an attachment tab with additional documentation and reference materials for your perusal at your leisure. We value your thoughts, so at the end of this presentation, please take the time to provide us feedback using the rating tab, and we will use it to improve future webinars. Today, we are pleased to welcome Ori Modai. He's the VP of R&D at Iguazio. Ori has a deep technical knowledge in designing and developing communication systems, and he has a vast experience in R&D management, wide-scale software and hardware projects, as well as architecture, patents, and developing new technologies. Prior to being VP of R&D, Ori was the CTO of RadVision and a board member of IMTC and UCOF. Ori has a bachelor's degree of science and computer engineering from the Technion Israel Institute of Technology. Welcome, Ori, and thank you for joining us today.
Thank you very much, Deborah.
You're welcome.
Thank you for the introduction. I'm very excited and pleased to be here. Along with me, I've asked Daniela Alper, who is heading the Iguazio marketing and is a known Flash enthusiastic, to join into this session and take this as sort of a joint stroll through what we've done here at Iguazio to enable big data and the traverse of big data from the age of batch processing to real time.
Hi everyone, so I'm Danielle, I'm here too.
So we are indeed in an exciting era of the big data in the big data arena. Some would classify that as the third generation of the big data evolution, which typically started. People highlight that big data started about 15 years ago when the first pioneers of the internet era started to cater for service to hundreds of millions back then, hundreds of millions of users, and enabled all the amazing tools that has driven and drove the evolution of big data till now. Some find the era nowadays a transient era of big data from being a sort of a tool that helps driving business to a tool that generates business by shifting businesses and decision making from from batch processing and longer term kind of processing and analysis to real-time reacting on real-time events in real world, and combining that with AI and machine learning. This is the era basically that Iguazio was born into and was as placed as a goal to help transitioning customers and businesses through this evolution and revolution. One of these customers, basically, we've got a few. One of the examples for such customers come from the smart mobility world, a huge and a very big and evolving market that relies heavily on the ability of the business specifically, to drive real-time decision-making and enable different applications and services reacting on real-life events. The most basic one being people hailing a ride and trying to reach from point A to point B in the quickest manner and the lowest price possible. Now, being able to drive this service at the basic level is something that one would find sort of a big data challenge, a standard big data challenge. But when you look at such a customer or such a service provider trying to be competitive in the market, this drives a new and exciting different use cases that requires the ability to react in close real time on people asking for service.
So you're talking about companies like Uber when you talk about ride.
Yeah, definitely. Specifically, we're not working with Uber, but we're working with some of their bigger competitors.
We've worked in Southeast Asia.
Yeah.
We have a couple customers in Southeast Asia, and so when you talk about a ride-hailing app, you're talking about any app, a mobile app mostly, right?
Yeah, I would bet at least one out of two people here riding a ride in the Far East right now are in one way or another interacting with services enabled by Iguazio. And one of the key drivers that or challenges, I would say, that these customers faced, and we helped them overcome, was the ability to do things like search pricing and the ability to correlate events in real time in the real world and their reactions basically through the interaction of many users with the application. Other things are like calculating in real time driver incentives and bonuses, or optimizing routes and shifting traffic through the city. Now, this is one of these customers was heavily relying on AWS and was taking the traditional big data approach. So basically taking Redshift and doing different analytical flows and trying to implement this traditional flow, but handling real-time events. So basically trying to determine, for instance, which are the most crowded locations holding more customers and where the drivers centered in the city, and trying to route the drivers to the right places while trying to benchmark the prices to reflect the demand and the response for the demand across the network. And of course, they were unable to do that using analytical flows when it comes to hundreds and thousands of IOPS running in their network.
And so this is a heat map. Can you explain?
Yeah, essentially one of the first things we've done with this customer and requires basically trying to ingest in real time hundreds or thousands of events and updates per second. We've managed to build a view of the world, of the current situation of the demand versus the response, and we're able to highlight the hotspots. And as you can see, this is if some of you with the keen eyes can probably identify Singapore here, and the huge hotspot at the right side of the map is next to the airport of Singapore. One would say that that's sort of predictable, but as you can see, what we've overlaid is the demand for rides versus the availability of drivers, and then you can see this allows basically the drivers to determine where would be the best place to park and wait for rides, basically, and on the other hand, this allows the operator basically to get a very clear view of the rush hour and build up an algorithm that determines the right pricing for each ride. Now, when it comes to implementing this in the real world, one would need a completely novel approach. The approach relies on in our perspective, on three basic elements. The first one is the ability to deliver high performance, and we're dealing at hundreds of thousands of IOPS per second on a basic cluster, combining that with flash memory. So one would say, okay, why not pull up an in-memory cache system, such as, for instance, Redis, which is a very known and established tool. But then when you try to implement that and still maintain persistency, this is something that pulls this kind of tools and this entire class into a place where it's quite challenging. And so this is one of the key enablers, is the ability to deliver a wide variety of data services while combining flash and NVMe technologies and high performance computing and networking and all of the required pieces, which we'll highlight in the presentation. The second thing is delivering a cloud-like experience, so a wide variety of APIs, standardizing on APIs, so the ability to have a wide variety of open source tools that can interact with the platform. and the ability to deliver a cloud-like experience in terms of the ability to build up an application very quickly and reacting on the demand of features and the ability to roll out features just in the same way that one would do when using a cloud service. So how do one can deliver on such a promise? And basically there are three. There's a key tenet that differentiates the novel solutions from the traditional ones. And the traditional approach would be, okay, let's take a high-performance tool, a database such as Cassandra DB, for instance, that was built to run on top of any storage facility. It can run on top of a network file system, on top of a block storage, a RAID-based block storage, network block storage, or it can run on top of a high-performance NVMe. But the reality of it is that if one would expect Cassandra DB that runs at tens of thousands of IOPS to run 10 times faster when using 10 times faster storage facility, let's say shifting from a standard SSD to a high-performance EMC or a XIV-based flash-based array, one only gains just a few tenths of percent. And this kind of disappointing experience comes from the fact that the tool is built to work with any kind of underlying storage device, and works very hard, and within its architecture there's an embedded premise that don't use the storage, don't assume that you can work with an hard disk, assume that you can work with an SSD or an NVMe, and do your best and do a lot of computational work to avoid hogging the storage or trying to minimize the work with the storage. So it means that the storage takes about just a very small percent of the work that the overall work that the database will actually do, and in such a way, if you optimize this small amount, you get very small gain. While in the new era, the new set of tools such as the Iguazio one can take a completely novel approach and re-engineer the entire stack. So the approach we took basically has a three-tier approach. We've got a standard API layer that is distributed and detached, scaled out by itself from the core of the storage. The core of the storage rides on top of a highly tuned database engine, on top of which we've built many data modalities. I'll get to that in the next slide. And that rides directly on top of NVMe. And the key differentiation, or the key technology highlight that the NVMe brings to the table is the ability to load hundreds of thousands of IOPS basically on a standard server, NVMe-based server. While utilizing high-performance NVMe's, you get random access, high-performance, the ability to do a lot of IOPS basically at a very low latency, and the ability to basically write to these kind of devices without being too worried about flash memory wear factor, by the fact that NVMe drives is basically targets a very high drive writes per day endurance level. And based on that, if you even detach the underlying storage, and this is also something that I'll highlight in the next couple of slides, then you get to a level where the same core, the same metadata core, the same database management core can work with different level of different tiers and different levels and types of storage, depending on the access pattern that is required. Basically, you can use NVMe's for very hot data, and you can use cloud-based storage for cold data, archival data, and so on. This transformation in the stack basically embrace the ability of the underlying storage all the way up to the upper layers of the storage stack, thus leveraging the ability of the underlying storage to the maximum possible extent.
So
Yes.
At Iguazio, how long has it taken to make the transition from thinking traditionally to coming up with this novel approach that's different and faster and obviously the future?
So I would say we had the benefit and the luxury basically of being born into the NVMe era. So, and one of the key things that one of our founders, Yaron, our CTO, have identified is the opportunity to combine the NVMe technology. Iguazio was born when NVMe was just sort of rolled out to the market, combined with high-performance networking and with careful software engineering, something that we've built a special team for that purpose, we were able to generate a pipeline that utilized the entire stack of capabilities in the hardware to the maximum extent, something that eliminates a lot of bottlenecks that one would face when working with the traditional architecture. So when it comes to designing or leveraging these hardware capabilities, there are three design principles that you need to put into place when you build up the solution. The first one, and maybe the most important one, is to leverage the parallelism of modern architectures to the maximum extent. That means that within the data pipeline, you need to engineer the front end, the data front end, to be able to run it continuously, while these services should never block, never lock, and utilize parallelism to the maximum extent. So eliminate all locking and make sure that in order to address an IO request, you are able to route the IO request directly to the service that will service that without interacting with any other services, and in parallel being able to truly distribute the load between many such services. So you'll be able to scale out from a very modest, small 3-node cluster or 1-node cluster to tens and hundreds of nodes running in parallel, thus essentially delivering endless scalability. Now, in order to further optimize on that, you need to look at different aspects of delivering the I/O. Things like latency optimizations. One of the key elements that modern applications look at is trying to deliver a low latency, and in parallel also predictable latency. Something, for instance, that a data pipeline engineered on top of Java is very, it would be very challenging to deliver that because of the Java built-in garbage collector. And as you know, many of the big data tools out there are Java-based, for instance. So this is something to consider when you start to and work on such building up such a data pipeline. The second thing is quality of service awareness. Things like once an I/O reaches once you are capable of answering an I/O, you should probably take into consideration trying to get all the I/Os as quickly as possible addressed from the system. In parallel, being able to balance things like differentiating different applications according to quality of service ranking or definitions by the user. Now, users nowadays look at both security and quality of service as things that they are looking for as built-in their data stack, something that if not pre-engineered into the stack is very difficult to deliver. And of course, all the basics, so making sure nothing actually locks, so you don't need to lock on anything. Being able to preempt memory management from the kernel, and so on and so forth. So these are the basic stuff that will enable the core to utilize all the cycles without basically introducing bubbles in the compute data pipeline. Second thing is you'd like to make sure that this 100% utilized CPU is doing only meaningful work. So eliminate anything that is wasteful. Things like making sure that the cache memory of the CPU is truly optimized, and that you can hint the actual processor, which memory the code is going to address, and making sure that the latencies incurred by memory cache misses do not occur, basically. And another thing is end-to-end zero buffer data flows. So imagine modern NICs, RDMA-enabled NICs, and so on, are capable of taking the buffer coming from the remote server through the network and placing that directly into memory. Now envision the disk, the NVMe disk, has its own DMA engine capable of taking the buffer and putting that into the flash memory. Now imagine an application that can tailor that end-to-end, so that the actual processor needs to take care of metadata and doesn't need to care about manipulating the actual bytes in the memory. Things, by the way, that are sort of accelerated in many architectures, such as CRC calculations, SSL acceleration, and encryption, that being. Things like data signatures and so on and so forth, things to look at trying to optimize the data flow. And of course, you'd like to, as much as possible, bypass the kernel, bypass the OS. The OS is there only to help you manage the application. The application needs to boot up and take control of everything that is running on the machine. Otherwise, the kernel has its own opinion on what the CPU needs to do. And you don't want him to do that in an unpredictable way, impacting performance. The third design principle, mentioned a little bit, I touched on that just now, is to leverage hardware to the maximum extent. And for that, I have to thank our kind hosts, Intel, for basically delivering year after year innovative features within the chipset, the CPU cores, the NVMe, the flash memory, and so on, to enable offloads from the CPU. You'd like the CPU to do only data control and management, and the smart calculation that relates to the business logic. You don't want the CPU to spend any cycle on actually manipulating the data. At Iguazio, we leverage everything that you can get from the CPU. We joke that we test the Intel CPU to the maximum it can deliver. We use everything from RDMA technologies, things embedded in the NVMe stack, such as and things that are actually starting to pop up on 3D Point enabled firmware, all the way through AVX technologies, vector processing for things like search and indexes, doing digests, calculating pre-filters and hints on the data, and everything that can help us to deliver more IOs out of the hardware and maximizing on the cost that we invested in the hardware. And last but not least, something that is dear to everyone that has touched in their career network technologies, balancing RQs, throttling RQs, making sure that the CPU is working as much as possible on meaningful work. So these are the key three design principles. If you're into designing high-performance applications and specifically manipulating data or moving data across the hardware, these three key elements should be handled in your design. Now, when it comes to deploying that on hardware, you need to make sure that you don't cross any hardware bottlenecks. And this is, for instance, an end-to-end dissect of the data flow through the Iguazio system. So we've got a node running the API service, a node running the data flows. They're all interconnected with a 100 gig enabled fabric that is, of course, RDMA enabled and so on, and is built to take the I/O all the way from the application landing in, for instance, a web engine enabled through an Nginx plugin, leveraging the SSL acceleration embedded in the cards or in things like Quick Assist, through the fabric all the way to the software controllers getting the I/O, sort of routing that to the right disk, doing the necessary indexing and landing that on the NVMe, and all that without crossing any QPI lanes, with minimal, with the processor touching as few as possible bytes in the memory, in order to maximize on the cache performance in the CPU. What we've done, by the way, and this is something that relates to open source that might be useful for all of you. First of all, we've got our own GitHub. We've got a few GitHub public repositories. I'll touch two of them. One of them is v3.io. v3.io is a sort of a collection of all the tools that we've open sourced that relates to interfacing with the Iguazio system. Two key highlights from that repository, things that we urge you to try out. First one is the Excelio project. It was originated by Mellanox, who are our dear friends. And since then, we've got our own fork that we were maintaining continuously. You'll find there an RPC high-performance enabled, RDMA enabled library that one can use in order to develop high throughput applications that can traffic data across the network at super high performance with very low overhead on memories. Another thing is, another project that is worth highlighting is HTTP Blaster. One of the the paradoxes that we've hit is that we're building a high performance application, but the existing tools in the market are not performant enough to challenge the system. And one of the funniest stuff was that we've tried to test our brand new Amazon compatible web APIs, data APIs, and we couldn't find a tool that can load the system at hundreds of Ks of IOs without building up a wide array of tens of servers in order to load one server of Iguazio. What we had to do is build up our own tool. We decided to open source that with the hopes of other people in the community finding that useful and also potentially contributing to that. So I urge you to visit v3.io HTTP Blaster and either feeding us with feedback and ideas for features, and also using that when testing your own applications. Just be careful not to deny of service any real-life website, please.
But so the HTTP Blaster is super cool and very useful. Are you going to say anything about Nucleo later?
Yeah.
You are? Okay, because we have one other GitHub sort of open source project which we'd love for people to look at as well. So
yeah. So I'll get to Nucleo at the end of this presentation, but Nucleo is our serverless framework project that we've open sourced. And the HTTP Blaster was instrumental in our ability to tune and test and tune its performance to hundreds of Ks of IOPS, while and proving basically that it's a few hundred times faster than AWS Lambda, for instance.
But you could use it also without, not just for AWS, for Lambda. You could use it.
You can use it anywhere. Yeah. So just to highlight on this flow, a few things we've done, for instance, is the ability of the packet or the request to land at an SSL accelerated NIC, landed the Nginx plugin, basically being leveraging the Nginx architecture or parallel architecture, transforming into an API towards the Iguazio system. We use Excelio. We also use another project that is worthwhile mentioning, Captain Proto, which is sort of, I call it the young and cool brother of Protobuf, which was built to deliver high-performance serialization, deserialization of messaging, landed a given core and directly writes the data directly to the NVMe that is directly attached to this specific CPU running the core. So this is something we've invested a lot of work to tune, and we were able in some workloads to reach up to 1 million IOPS on a given core. leveraging, delivering 100 gigabits per second at less than 1 millisecond, 95 percentile performance. So this is indeed an engineering feat, I would call it, as I call it to the guys.
So you basically, the difference between, because you took a very complex slide, and can we just see again what you added in the second stage? You added the connections there.
Right. So on every link, and I believe you can download the presentation afterwards, you'll see a highlight of how the design principle come to practice in a real life world system. And another interesting approach we've taken, and this is something that relates to data manipulation, data platforms in general, and I urge you basically to consider, is careful tiering and detachment of three basic tiers in the architecture. The first tier is the ability and running at the core, the middle of the slide, is to be able to detach the metadata core that holds the indexes, the access structures that allows an I/O to be basically served based on its key and so on, and its parameters, to detach that from the flash, from the storage layer and the API layer. What we've done is sort of abstracted the core using our v3.io API layer, and on top of that, we've taken a collection of open source tools and projects and adjusted that using their built-in plugin capabilities, such as the Nginx plugin and so on, to be able to deliver a wide variety of tools that can interact with the system. So this approach is very useful to allow you to basically interconnect new flows very quickly, or being able to deliver new APIs and new services on top of a single core, unified core. Another approach that we've done by detaching the core from its underlying storage, we're capable of delivering both the tiering by access pattern, by access frequency, and directing the data to the right underlying storage that will utilize the underlying storage to the maximum extent. For instance, we're capable of identifying a random access object and putting that directly on NVMe if it's being accessed very frequently, while taking a log-based workloads, things like logs or a queue of messages, and basically tiering that towards colder kind of pattern, access pattern enabled storage, such as rotating disks or JBODs, or even the cloud storage such as S3 or Glacier or Azure Blob. So by the ability to detach the management, the data management layer, which is the middle section of the diagram, the API layer, which rides at the top side, and the data, which rides at the bottom side, we're capable of optimizing the workload and utilizing the hardware to the maximum extent, and delivering the best cost performance that the customer can ask for. Now, one of the key, we're at the age, being a parent to young kids, one of the things I find it most challenging, trying to sort of educate them how to properly behave in a digital world. And one of the key aspects is maintaining personal information and behaving correctly in the web. And being a sort of a data platform vendor, we found ourselves, or basically we challenged ourselves to enable our customers a wide collection of security tools, to enable them truly to be able to enable their customers or the customer by itself to be able to differentiate, to classify and differentiate which data can be accessed by whom and what kind of operations can be done on every data element.
So it's a form of parenting, that's what you're saying.
Yeah, it's a form of enablement, I would say, enabling our customers to be proper parents to their data.
Okay.
Now, this is a key aspect, and this is one of the key challenges in big data pipelines. Modern data pipelines are sort of architectured in the Lambda architecture or Kappa architecture paradigm, and involves combining many tools. Now, as you know, security is all around the weakest link kind of approach. So if the data resides in one system out of many systems that has very poor security or very poor security policies enforced, you will end up exposing the data through this weakest link, through this copy that resides on the weakest or the poorly configured system. So one of the key features of the Iguazio system, and one of the key challenges, technical challenges we had to tackle, was to build up an engine that is capable of classifying an I/O that comes into the system by many aspects that relates, many properties that relates to this I/O. Everything from where the requester is. I would like, for instance, Daniela, when she sits at home, not to access some very confidential data of the company, being responsible for IT as well. I have the luxury of doing that. While in parallel, when she sits at the office, I'm okay of her accessing anything. So I'd like to see where the request is coming from. I would maybe like to disqualify requests coming from China or from some remote place where I wouldn't expect someone to access the most secure data of the system.
So we see this with financial teams that work together globally,
right,
where they're looking at the same file, but each person, depending on their global location, has access to different parts of that
right
data.
So another thing is the target path or the table name. So I would like, for instance, everyone to address the phone book table that holds all the phone numbers of all the employees of Iguazio, while the table that contains the financial data of the customers should be masked in case someone that doesn't have the credentials is trying to access the field that contains the credit card number. So essentially, the data architecture should intercept, the data engine should intercept an I/O classified by many properties, sort of a firewall for I/O if you want, and then decide what to do. So trigger different operations. Things like the basic ones are admission control. Should the person be able to read the data, write the data, maybe address only parts of the data on certain fields. So that's sort of a fine-grained filtering. Being able to decide what is the quality of service rule that should be applied on the I/O based on the application that generated the I/O, and potentially trigger different operations that should run in the background and do some audit operations.
The alternative in the market to this is copying files and deleting certain parts of them. What Yaron calls managed copy services, where you just copy stuff over and then it's even less secure.
Right. So I've seen people do funky stuff trying to overcome security because security is sort of the threshold condition of deploying a data service. Things like copying data about 4 times because I've got 4 different departments, each with its own different restrictions of levels of accessing the data. I've seen people avoiding tools because they don't have any security in place. And I've seen people basically not implementing business flows because of the security threats of exposing data.
So they'd rather just not do it as long as they don't sacrifice it.
They wouldn't do it until they know that they can secure the data. And in order to deliver that, what we had to build is basically an engine. What we do is we take the rules definition, which are sort of service to the end customer, sort of like a firewall set of rules, and with the first match kind of principle. And if an I/O hits a given rule, we need to execute on the attached operation. So the first thing you need to do is take this flat, user-friendly, human-readable, human-comprehensible representation of set of rules and transform them to something that the CPU can actually execute. Specifically, the typical methodology in the market is doing a set of selection trees or classification trees, and running them as sort of a forest. So trying to optimize on the high disqualifying rule first. So this is the first step. Then one would need to compile that to something that the CPU can actually run, taking into consideration memory constraints, minimizing the amount of operations you need to do in order to basically classify the I/O. And then you'll end up with a structure that the CPU can traverse on, and then execute that per request. And doing that at hundreds of nanos of per classification, that is sort of a challenge. I do urge you to take this into consideration and always remember yourself trying to maintain your own privacy. And when it comes to building up products and building up services, try to make sure that you build in the right security into the product to enable your customers to be able to secure their data, secure their service, and minimize the exposure to security threats. Last but not least, we consider ourselves evangelists of the transform in the storage domain. Till 5 years ago, 3 years ago, when it came to enterprise storage, by default, the discussion went to what kind of wide storage, block storage array are you using in the enterprise? What kind of features are you interested in? dedupe, and all of that stuff. We're huge evangelists to the transformation from block storage to object storage. The key benefits of this kind of transformation is first and foremost the ability to have an efficient abstraction. You don't need to worry about plumes and block addresses and all of that stuff. You've got an address. The address represents it's human readable. It represents a piece of data that can be of any size you need, and can hold any data and any metadata that you need. And every operation that you do on that can be atomic and asynchronous. And the underlying storage will take care of that. And one of the key design principles we've done on the storage layer was to take any underlying storage that we use and abstract that using some software to a key value kind of access. That allows me to abstract many things on the application level, and things that typically you would worry about is making sure that the applications that address the block storage array does not step on one on top of the other, making sure that you've got your own kind of fancy locking mechanism put aside in order to make sure that each initiator has its own unique keys and they don't overlap themselves. Using a key value abstraction simplifies applications and allows applications to truly utilize and truly build itself as an asynchronous end-to-end flow. This kind of transformation allows you is sort of we're capable of doing that by building an abstraction layer on top of the underlying storage. So what we have done basically is we've built a set of abstraction layers. Well, the basic API is sort of the most trivial one we found, which is the object store API: get, put, list, and delete. And what we're doing using this API, what we've done is built a metadata layer, which is of course high performance and as one would need it to be, and allowed the application to address using a key that can describe a given piece of data. Using a key, you can simply access the data, and we guarantee that the operation would be atomic. So as you can have multiple applications doing parallel put operations, update operations on a given piece of data, what we guarantee is that every put when is done at sequence and they don't trap one on top of the other and being meshed up together. Now, in order to do that, you need a metadata layer that has the data structure that allows you to transform a key to an addressable piece of data that is actually stored somewhere. And the other piece that you need is to be able to deliver all the features that an underlying storage will need. That would be encryption, error resiliency, error correction, and so on and so forth. Now, using this key value-based approach, one can start to do things, fancy stuff like data mobility, data migration, and so on. All these advanced operations are done on the key level. So we urge you to consider this architecture, and I urge you, maybe it's worth to attach my email. I would welcome any questions, any basically discussion that you'd like to steer up after the session on how to enable this kind of new workflows. We as storage consumers basically would be very keen on storage vendors adopting this approach, basically enabling new advanced APIs on top of the underlying storage.
So let's just say your name is Ori Modai, and the email is orim@iguazio.com. So that's ORIM as in Mike at iguazio.com. And of course, you can always reach Ori through the website. And then there's a poll here now.
Yeah, actually, I mentioned that. We'll do it in the end.
Okay. Yeah, that just sort of popped up on my screen. Okay.
So when it comes to implementing the high-level API, one would need to develop basically an object storage device abstraction. The object storage device basically is capable of getting an API call, a get or a put, that interacts on a full piece of information. So the API is sort of atomic and works on the entire piece of object at the same time. That allows us to decouple and maintain atomicity in an efficient way. And then you'd like to decouple the way that the data would go to the underlying disks from the actual implementation. So if you've got rotating disk that needs to consider the movement of the head across the plates, or you've got an SSD that needs to worry about a wear factor, or you've got an NVMe that simply needs to utilize maximum random access, then you can sort of decouple that from the API and tailor that to the benefits of your device. The actual abstraction only needs to take care of the addressability to the data, implementing the different advanced capabilities. Some devices would have built-in encryption, some would need to do that as a service on the software level, handling error corrections and so on, and adjusting protocols. But basically, this is something that can be easily done. And before we shift to the questions, and I'd like to get a small poll before we shift to the questions, I'd like to mention another project that we've done. It's sort of we started that as a key enabler for delivering serverless functions, serverless workflows, which we believe would be the next generation kind of way to implement big data flows. What we've done is we decided to open source that, since we found the availability of such tools as lacking. And you can find our serverless framework, which is steering a lot of interest and a lot of corporations, even from the big players, the cloud players such as Microsoft, that actually contributed to the project, at the GitHub repository called Nucleo. What we've done is implemented in this project all the design principles that I've mentioned throughout the presentation. So building up, maintaining parallelism to the maximum extent, making sure that you don't block where you don't need to block, doing things asynchronously, and scaling out, addressing, and delivering elastic computing. So all of these principles were implemented also in the core of Nucleo. If you're interested in serverless functions, I urge you to visit the repository. You'll have a lot of examples and documentations found there. And just to give you the highlight, the Nucleo core is capable of handling 400K events per second, addressing HTTP requests basically at 0.1 millisecond latency. And the entire core is written in Go. And that is about 50 times faster than Amazon Lambda, and almost 100 times faster.
And it can work not only in the cloud.
Right, yeah, and you can basically download that, run that on your Raspberry Pi, Mac PC, maybe your TiVo, or at the cloud, actually, and leveraging that and doing that, implementing advanced data flows. And with that, I don't know, do you know how to run the poll?
I think Deborah needs to run the poll.
So before we shift to the Q&A section, I'd like to run a small poll on how fast do you believe the Iguazio core runs? Deborah, can you run that?
Yeah, it's available for the audience. Do you have it on a slide that shows the choices of the answers?
Yeah, it's I see it in the votes from the audience. I urge you while we take the questions to vote, and let's see how fast you think we are.
Yeah, but it's not. We don't have it on the
start
slide.
Voting. Maybe I need to do this. Okay, I started the vote. Okay, so and with that, I'll shift to the questions. Any questions from the audience, please?
Yes, we do. What are the challenges when working with a standard storage and file system?
That's a great question. So I turn you to there's a very interesting Intel research taking a simple echo hello world into a file on top of I believe it was ext2 or ext4. And what they found is that in order to write down 13 bytes of data, you need to do about a few tens of Ks of I/O bytes, basically writing tens of Ks of bytes and doing about 13 different I/O operations within the actual file system. And that is the core problem of modern file systems. The fact that you need to maintain things like locking and journaling and all of that becomes a challenge when you've got your application, in this case the simple echo into a file, running on top of many layers of file systems that needs to consider very generic and wide different use cases and flows. So that is the key, and by basically re-engineering the stack, one can truly utilize the benefits of modern hardware architectures.
Yeah, another question for you. Shouldn't higher level abstraction reduce performance?
That's a great question. So the traditional view of the world was, I don't want to use the NFS, I don't want to use an S3-like tool because it's slow, because it has a lot of layering, a lot of logic inside. But I do believe modern platforms such as Iguazio, and there are a couple of more maybe you can find, I don't know, taking the right approach in the architecture level can actually mitigate that and deliver, like we do. We deliver about 500K IOPS on S3-like workflows that of course delivers the entire complexity of S3 and advanced APIs that S3 has to offer, and it's somewhat equivalent to the performance of the highest performing block storage, which up until a few years ago was considered the highest performance tools out there. So I do believe now there are tools such as the Iguazio one that can allow you to handle very high performance workloads without compromising on the software abstraction and services that you get from the data platform.
Okay, we have another question. Why should you decouple APIs from the database?
Yeah, that's a great question. One of the key challenges when trying to go into a customer that started its work, its baby step into the big data world, that you always find something there. And on the other hand, different customers would like to have a wide variety of APIs and tools to be able to work with. And by abstracting the API layer, what you can gain is widening the ecosystem, widening the available tools that you deliver to the customers. For instance, we've got customers that has a development team running on top of Iguazio that only knows Scala and can work with that. And we've got other customers doing Python. We've got customers doing REST APIs such as the AWS compatible APIs we've got in the platform, while others do only Spark jobs and Presto queries. So a wide variety of APIs increase the flexibility of the customer, reduce the complexities, and at the end of the day allows the customers to reach the market as soon as possible. And that is what we've got as sort of the key goal for us to enable.
We have another question. Sounds like Iguazio provides scale-out object storage and no SQL type DB?
Definitely. We've got, at the core of the system, we are a NoSQL database. On top of the NoSQL database, what we've implemented is other flows such as streaming and object store-like flows, and even file flows. So you are capable of, and we've unified them all. So you're capable of going into or browsing into an NFS mount on top of the Iguazio system, doing an LS on a table that is an actual database table and seeing all the primary keys, and in parallel ingesting data from any API that you'd like. But at the core of the system, we are a scale-out NoSQL database with the object store capabilities.
Last question. Besides price, what are the advantages of using NVMe as opposed to NMemory?
That's a great question. So essentially, price is the biggest obstacle of leveraging and building large-scale, persistent, high-performance data solutions. And the price performance improvement between DDR-based solutions and NVMe-based solutions is about 1 to 20. And of course, NVMe's, as you know, we've emerged out of the NVMe shortage crisis that we had last year, and finally, really, NVMe's are decently priced, available to anyone that needs readily available technology. And I do believe that anyone trying to build up a persistent high-performance data solution using non-volatile DRAM would find it very hard to scale because of the price. And also, I would argue that you wouldn't be able to deliver rich API and rich performance and a really scalable solution based on that.
Lastly, you want to give the audience what the answer was to your polling question of what is Iguazio's maximum speed? What is the answer?
So everyone got it right. 1 million IOPS per second on some of the workloads, and I do urge you to try it out and see it for yourself.
Well, that wraps up our question and answer portion of the presentation today. Thank you, Ori, and thank you to the audience members for joining us today. Be sure and provide feedback about today's webinar and check out the schedule for upcoming webinars. Thank you and have a great day.
Thank you, Deborah.
Thanks.